Hi there, and welcome to Mr. Carlson's Lab. In a previous episode, I posed the question to see how many of you out there would be interested in a scratch build of a Nixie tube frequency counter, and the response was really quite overwhelmingly positive. So that's what we're going to do. Now, for those of you that are uncomfortable with the high voltage involved in Nixie tubes, what I'm going to do through the course of the next couple of videos here is show you how to also use 7-segment displays in this frequency counter, or even if you want, just have the thing read out in binary. Now, this is too much to do in just one episode. I can't do an entire frequency counter and really focus on all the little things that we're going to be looking at. So this will probably be like 3 parts or something like that. So maybe we'll start this one off as understanding the Nixie tube, and the next one might be the oscillator, and then the third one will probably be the digital section, and that should be it. So that allows me to focus on every individual part and be really thorough with the explanation rather than just cramming everything into just one episode. So let's get started with understanding the Nixie tube. In order to better understand the Nixie tube, what I'll do is I'll draw the schematic diagram and we'll take a look at that. So when you're looking at a schematic, the standard diagram for a Nixie tube is an oval with an upside down T. The upside down T is the plate or anode, just like in a normal vacuum tube. On the bottom of the Nixie, you'll see a bunch of circles with lead-out wires. Depending on the manufacturer, sometimes they'll even write in the numbers. Sometimes those little circles are drawn as little cups too as well. Again, just depends on the manufacturer. Now, before we get too far into the Nixie tube thing here, you need to understand that Nixie tubes are neon-filled bulbs, and they require high voltage to make them glow. So if you're unfamiliar with vacuum tubes and high voltage circuits, I strongly suggest that you don't build this. You should familiarize yourself with high voltage and vacuum tube circuits before you attempt any kind of circuit like this. If you're following along, you're doing so at your own risk. Just take care. Throughout the process of this video, I'll also show you how to use 7-segment displays, or even, as I mentioned earlier, have the frequency counter just read out in binary. That looks pretty neat as well. So if you're uncomfortable with using Nixie tubes, there are other options that are low voltage options as well. Alright, so what I'm going to do here is I'm going to draw the current limiting resistor in the top here. This is just standard stuff that you'll see in a lot of frequency counters and digital multimeters and things like that. So this is just kind of a standardized circuit here just for ease of understanding. Real standard value, 22k ohm resistor. Real standard high voltage value, 170 volts DC. It has to be direct current. If you put AC there, it'll look like a big fuzzy mess inside. So it has to be direct current. Now, the whole idea of this resistor up here is to set the amount of current that this tube is going to have to deal with. Now, as a rule of thumb, you really don't want to exceed about 3 milliamps. Now, the way to tell if you're overdriving your Nixie tube or giving it a little bit too much current is if the Nixie tube numbers inside aren't glowing a nice red-orange color. If you see them start to glow kind of a pink-looking color, you might be giving it a little bit too much current. If you give the Nixie tube too much current, just like anything else, you're just going to shorten its lifespan. So through the course of these videos, I'll also show you, without actually knowing really any specs about the Nixie tube, how to set the correct current for that tube. So this will all just fall in line with this series. Now, Nixie tubes are very easy to operate, probably easier than a 7-segment display even, aside from the high voltage supply. All you need to do to light up, say, the 0 inside is just ground the corresponding lead-out wire that connects to that 0 or to that cathode inside the tube. So you ground it out and the 0 is going to light up inside. If you ground out the 1 will light up. Now, all the rest of the pins have to float, and whatever pin or whatever number inside that tube you want to light up, you ground out. Now, I've only drawn to 3 here, 0 to 3. It's actually 0 to 9. And depending on the Nixie tube you have, some of them will have a decimal inside of them as well. Some do, some don't. Again, just depends on the tube that you have. Now, in the late 60s, 70s era, they developed an IC to control this Nixie tube a little bit easier, and it was called a 74141 IC. And really what it is, it's a BCD to decimal decoder with a high voltage transistor array inside it. So they kind of took a whole bunch of things and just put it all in one IC. So what I'll do is I'll just draw that IC as a rectangle down here. So you have a whole bunch of pins on that 74141 IC that connect to all the pins on the Nixie tube 0 through 9. And then you have, on this side, you have A, B, C, and D. So that's the binary coded decimal side. So basically you're taking 4 lines and you're giving it different combination of highs and lows to light up the certain number inside the tube. Now I've explained how this ABCD, this binary coded decimal, works in a different video, and I'll link that just below the Show More tab. But throughout the series of these videos, we'll be going over that as well anyways. I won't go, as much in depth as I did in that video, but you should still get the understanding. So that's one way of controlling this Nixie tube. Now, the 74141 is getting kind of hard to get, and there is a Russian variation of it that I believe is probably almost just as hard to get now. If you can find them, it makes controlling these ICs a little bit easier. They are DIP packages, so they're kind of a big package, but it's still smaller than using transistors in another BCD decoder. But I prefer using that method anyways because they're all readily available parts, and they're relatively cheap. And they also deal with high voltages a little bit better than the 74141 or its Russian variation. So what I'll do is I'll just draw that configuration right now. So I'll just erase this here, give myself a little bit more room. So just say I'll just draw the cathode or the number inside the tube. So considering the tube is like this and we have a whole bunch of these cathodes inside. So what would happen is this would run down to an NPN transistor. That goes to ground, and then this is a resistor here in the baseline, and then we have a different BCD to decimal decoder that controls this transistor. Now that transistor is an MPSA42. It's a very common transistor, and they're commonly used to control Nixie tubes. The nice thing about the MPSA42 is it will deal with 300 volts or so. So if you're playing with your high voltage power supply, or you're dealing with Nixie tubes that are a little bit tired, this gives you a little bit more leeway to kind of critique things and light up those tired Nixie tubes. The 74141 IC is really suited for strong Nixie tubes, and if you get the voltages just a little bit too high, the transistors inside will start to break down and you'll start to get faint glow on other digits and things like that. This kind of situation completely avoids that. So I do prefer this. The only downfall is that if you have a 5-digit frequency counter, you've got 50 transistors that you have to connect up. All right, so there's basically 10 transistors per Nixie tube. It's because you have 0 through 9. Now the first Nixie tube, if you only want it to go up to say 30 megahertz, you only really have to populate, basically 0 to 3 if you want to have the 0 light up. All right, and if you want to say make this thing go right up to 99 megahertz, then you're going to have to populate all of them. So sometimes you can get away with reducing some of the transistors on the first Nixie tube. So the MPSA42 is very versatile. Now the BCD to decimal decoder is a CD, so that's Charlie Delta 4028, and that's a really common BCD to decimal decoder. So what happens is it's the same idea as the 74141, except we're kind of separating the BCD to decimal decoder and separating the high voltage transistor array from that one IC. We're just separating it is all we're doing. So whereas the 74141 IC will pull this cathode towards ground when the appropriate number is supposed to be lit, the CD4028, the output will go high. So that high is attached to the base, which turns on this transistor, which pulls the cathode low. So again, basically we're just splitting apart that 74141 IC and using a separate transistor array, which is a little bit more robust. Again, I do prefer this method myself. The CD4028 is very, very common IC. It's readily available, and so are all these transistors, so you don't have to search out any kind of hard to find ICs. So if we're going to use this transistor, we need this transistor to go into saturation. So we need the thing to act like a switch. And in order to do that, we need to figure out the value of this resistor here. Now, I can give you a bunch of shortcuts. Basically, a 10K resistor is going to keep this thing in saturation. You'll have no problems. Even a 15K will keep the thing into saturation. But for those of you that kind of want to do any kind of current pinching, and you really want to just keep everything optimized, what I'll do is I'll show you a bit of math in order to figure out the value of that resistor using an MPSA42, and you can use that math for figuring out this resistor for other transistors as well. I promise not to bore you with a lot of math in this video, but for some of you this may be beneficial, so I'll just quickly go through that math in this next step here. These are the steps to determine the value of this resistor in order to saturate this MPSA42 transistor. Now, when I say saturate the transistor, I mean that I want this transistor to be as fully on as possible, or as close to being a closed switch as possible. I do not want that transistor to operate anywhere within the linear region. If it does operate within the linear region, that means that it's acting somewhat like a variable resistor. And the only thing we want to do any kind of current limiting in this circuit is the value of the plate or anode resistor on the top side of that Nixie tube. And that was that 22K ohm resistor that we just talked about. So again, we want this transistor to be either on or off. We don't want it to be in any in-between state. So before we figure out the value of this resistor, we need to know a little bit about the circuit itself. So first of all, we know already that the maximum amount of current that we want that Nixie tube to deal with is 3 milliamps, and that will be set by that anode resistor. So the maximum amount of current across this MPSA42 is going to be 3 milliamps. The next thing we want to know is the worst case beta, or the lowest gain of this transistor, and that will be about 25. The next thing we need to know is the CD4028 IC. When the output is selected to turn this transistor on, what's the voltage going to be at that selected output? Well, it's going to be very close to 5 volts. We'll just use 5 volts for this example. So what you do is you take that 5 volts and take the drop across the transistor away from that, which gives us 4.3 volts. That's the next thing we need to know. So now we're ready to do our math here. So all we do is we take that 3 milliamps, divide it by 25, which is the beta, and we get 0.120 milliamps. That's the base current to turn on this transistor at this point. What we do then is we take that 4.3 volts and divide it by that 0.120 milliamps, and we get 35.833 K. And that's the value of that resistor to bring this transistor into saturation. Now you're probably saying to yourself, well, didn't you just say 10 to 15 K ohms? Where do we get 35.833 from? Well, this value here will bring the transistor just into saturation. So any kind of changes in the circuit could put that into the linear region. We don't want to take that chance. So we're going to give ourselves a safe zone and divide that by 2, which gives us 18 K ohms. And 18 K ohms would be the value that would safely keep this transistor in saturation. Now, this isn't a critical value at all because this transistor isn't operating at any kind of set point. It's basically just turned on hard. So it's just basically acting as close to a switch as possible. So anywhere between 10 to 18 K ohms will be absolutely fine to use with this arrangement here. So 10 K ohms, I wouldn't want to go much lower than 10 K ohms because, then we're starting to, load the output of this little IC a little bit here, but 10K to 18 will be absolutely fine. So if you have a bag of 10K ohm resistors, use them. If you have a bag of 15K ohm resistors, use them, or anything in between. It's absolutely fine. And that's how you do the math in order to figure out the value of this resistor right here. Here's an example of how these little MPSA42 transistors are controlling the digits inside that Nixie tube right there. So what's happening is every digit inside this tube is connected to a collector of one of these transistors here. So we have 10 transistors, 0 through 9, inside that Nixie tube. Right here is just a 4017 counting IC that's receiving a pulse from my pulse generator at about 1 cycle per second, and it's just creating a count, and the Nixie tube is displaying it. Now again, the reason that we have these MPSA42 transistors here is to isolate the high voltage that's available at the digits here from this IC. We don't want that high voltage getting into this IC at all, or it would cause damage within that IC. Now, when this IC is counting, what's happening is at every count, a different pin is going high. It's going to 5 volts. And that 5 volts is getting applied to the base of one of these transistors through a 10K ohm resistor here, and that's turning that transistor on. When that transistor turns on, it's simply just pulling that digit towards ground. So it's connecting the lit up digit that you see to ground here. And that's really just how this is working. So a lot of people put these little counters together in order just to display a Nixie tube or make Nixie tube testers. Now, I have this thing hooked up to a pulse generator, and I could very easily just put a 555 timer here or something like that that would create a 1 cycle per second pulse. So if you're interested in me drawing up a schematic or displaying a schematic for something like this, if you're interested in this, just leave it below in the comments, and in the next video I'll quickly have a schematic available on the whiteboard for you if you want to build something like this. Now again, keep in mind that Nixie tubes have high voltage involved. There's 175 volts at the top end of a 22K ohm resistor just right behind this Nixie tube here. So if you build a circuit like this, you're definitely doing so at your own risk. You need to take care. There's a little bit of high voltage involved there. So what I'll do next is I'll hook up a voltmeter and I'll just stop the count here. I'll remove my pulse generator here and I'll show you how many volts is actually at an open digit here, so one of the digits that's not being grounded out. I've disconnected my pulse generator here and it randomly stopped at number 7. So what we'll do is we'll search for a floating digit or a digit that isn't lit up here. So I'll just randomly pick one and hopefully it's floating. So let's try this one right here. Look at that, 111.48 volts. I can guarantee you, if these transistors weren't here, this IC would not like me very much. The next time I tried to turn it on, I don't think it would cooperate. So that's the reason for these transistors here, is to isolate these digits from the ICs. I've removed the 4017 IC here, and I've attached a jumper clip to the positive rail here just to demonstrate how 5 volts will turn on these transistors here. So what I'm going to do is just randomly choose a resistor here, and I'm going to apply 5 volts to the far end. Now by applying 5 volts to the far end of this resistor, it's going to supply enough current through this resistor into the base of the appropriate transistor. That's going to act like a switch, and it's going to connect the collector of the appropriate transistor to the emitter and ground out one of these little digits inside here, causing it to light up. So all of the emitters of all of these transistors are all hooked to ground, and again, all the collectors of these different transistors are hooked to different digits inside this Nixie tube. So this is 0, 1, 2, 3, 4, 5, 6, 7, 8, and 9. And that's how all those transistors are hooked up. So I'll just randomly attach this to, say, this resistor here, and that lights up the number 3. So this is 0, 1, 2, 3. So that little transistor right down there is turning on. So when I touch this right here, that 5 volts is supplying enough current through this resistor to turn that transistor on, effectively acting like a switch, and you can picture it connecting the collector to the emitter and grounding it out. And if I choose another one, it'll do the same thing. See number 5 there? Now here's the thing, if I was to go to the opposite end of this transistor here and touch this end, I would burn out that transistor because it wouldn't be able to deal with the amount of current. So that's the reason that we have these resistors in line with the base. We can't directly hook the base directly to 5 volts. What it'll do is it'll just cause the transistor to immediately burn out. So these resistors here are acting again somewhat as current limiting resistors as well. So we're giving the transistor enough current to saturate and to turn on fully, but not enough to damage the transistor. Thanks for stopping by the lab today. Hope you enjoyed this episode about understanding the Nixie tube. If you did, you can let me know by giving me a big thumbs up and hang around. I'll be making the next part to this video series very soon. So until next time, take care. Bye for now.